Hello, everyone in Business Cal. I hope you are looking forward to the rest of the semester as we begin our first real lesson here. So basically the format's going to be a lot like this. I'm going to have a video going through these handouts, and there will be a filled out copy so you can kind of like look and see it, follow along. I strongly encourage you to make sure that even though that is available to you, make sure that you go ahead and fill these handouts out as you go along, listening to the lecture. If you do this, it will definitely help solidify the material in your head. And also, of course, do not forget to do the homework on WebAssign. That will be very, very critical for your success. And of course, if you have questions, feel free to email me. And we will try and get our correspondence done that way. So with that being said, let's go ahead and get into this. We're going to be discussing the limits, and we're going to have an introduction to limits. This is going to be very important as we move forward, as we get into derivatives and other mathematical tools. All right, so the limit of a function is simply the value it approaches. Right? It's the value it approaches, not necessarily the value it equals. All right, these are two different things. The function will approach something, but it may not necessarily equal something. All right, so I want to call your attention to this. I've graphed on Desmos.com. As you can see, Desmos up at the top here. Very useful website. If you have not been here before, I encourage you to come visit this website. It is a free graphing calculator website, and I'll be using this a lot in lectures. So what we have here is a graph. It looks like a parabola. It is a parabola. You can look at it. The function being graphed is this right here. You notice that we have an x minus 1 on the top and an x minus 1 in the bottom. Now that means that whenever x equals, x equals, for any value you plug in here, these two values will of course cancel out, except when you get to the value x equals 1. And whenever you get to the value x equals 1, you'll encounter a 0 divided by 0 error, right? And so 0 divided by 0 does not exist. It's not a number. Like it's not defined. So anytime you come across 0 divided by 0, it's nothing. It's total, utter nonsense. If you want a humorous explanation of it, I suggest you get out your phone if you have a iPhone and ask Siri what 0 divided by 0 is, and I think you will get a very comical response. All right, so let's take a look at this. Here you can kind of click on this, and we can see what the x and y values are. And so it's going all the normal values of x squared until we get to right here. When we get right at the value 1, it becomes undefined, right? So that's the one and only point that it is undefined at. We can go ahead and mark this point, if we will, right there, so we can kind of see it a little bit better. And so if I asked you, okay, for this function, what does f of 1 equal, right? If you plug x equals 1, what do you get? It's undefined. But note, if I said, well, what about the limit? What happens as we get close to it? Not necessarily right on it, but just to the left or to the right of it. Well, it seems to be approaching 1, right? You kind of even see that right along here. So it is approaching the value 1, but it does not equal 1. Right? There's a very big difference here. All right, so back to the handout. Let's go ahead and take a look here at these examples. And so you can see the question being asked, what is the limit as x approaches 1 for our function f of x? And so you can see, what does this open circle mean? That means that the open circle means the function is not defined there. But what we're trying to find is, well, what happens as x gets closer to 1, from either side? Well, you can see that it is, in fact, approaching this value. We'll call that, it looks like 1.2 to me. We're kind of just eyeballing these for right now, just so we can get the idea, right? And so there's a big difference between asking this question. If we say, well, what is f of 1? Well, f of 1 is simply not defined. It is undefined. That's what UD stands for, undefined. Right? Okay, so let's take a look here. Now we want to know, what is the limit as x approaches 2? Right? As we get closer from this side or this side. So we're saying, okay, well, what's going on? We're coming along here. The limit, from either side, well, that is approaching this value. It doesn't equal that value, but it is approaching this value. It is approaching 2. Right? So this 2 is that 2 there. Okay. So that way there is no ambiguity. And note that if I ask, okay, well, what is, sorry, let me switch, there we go. What is f of 2? Well, it's going to be 1, right? Because then we're looking at that point right there. So, the distinction is pretty clear, but it's also, I know it's probably a little obvious at this point, but I really want to hammer this difference home, because we really want to make sure that we are aware of how to differentiate between these two. All right, so the next one, what is the limit as x approaches 3? All right, so we've got, we're looking for 3 here. There we go. Well, it looks like it's approaching this value here as we get closer from one side or the other. So it looks like it's 2. Now, if I asked you, what is f of 3, you would tell me 2 as well. So the takeaway here is that, the value, the limit and the function evaluated at that point are not necessarily the same, but they're not necessarily different either. They're just 2 very different questions, and oftentimes they will have the exact same answer, oftentimes they will not. Okay. So the above are all examples of two-sided limits, right? As we were approaching it from this side and this side, right? But limits can also be one-sided. And so we'll use a positive sign to indicate that we're coming from the right, and a negative sign to indicate that we are coming from the left. All right, so let's use this to evaluate the following limits. All right, so note in this one we've got a negative sign right there. So the negative sign is always put where the exponent usually goes. The negative sign means we're approaching from the left, from this direction here. And what value are we approaching? Well, we're approaching this guy right here. So it seems to be approaching 2. Okay. Here, notice same graph. Now we're approaching, we got a positive sign there. So we're approaching from the right, like so. And so we're here. And so the guy equals 1. All right, and then again, note we're approaching from the right again. Note for this specific example, it doesn't matter if we approach from the right or the left, but it is asking what happens if we approach from the right, and that looks like that's about 1.2, same graph as we've done earlier. Okay, so that's those in a nutshell. Now let's look at evaluating a limit when we don't have a graph available, when we have this expression. And note, this simply means that if x is less than 2, then you use that expression. If x is equal to or greater than 2, then we're going to use this expression here. All right, so the limit as x approaches 2 from the left. So I'm going to show you a little trick here. What we're going to do is just say, all right, this is very similar to saying what is f of 2 minus some very small amount, right? Some infinitely small amount, right? This number here is vanishingly small. Right, that's how we're going to use that one. So you can see, like, we're not at 2, we're slightly less than 2. So this is, you can kind of use this nomenclature in this way just to kind of help you understand what's going on. And so you can kind of think of epsilon, it's vanishingly small, right? It's never actually 0. It's always greater than 0. But it's always approaching 0, right? It's becoming small, but it's never nothing. Okay, so we're just, a little bit less than 2. That's all. And so now, well, given that information, which case are we in over here? Well, obviously, we're a little less than 2. We're looking at, 2 minus epsilon is right there. So we're a little bit less than 2. So we are in this case right here. So now we just look at this, and we're going to actually plug in the 2 to see where it's approaching. Right, because the epsilon is vanishingly small. And so we have negative 2 minus 2 squared plus 2. 2 minus 2 is 0, so we're left with negative 0 plus 2. The answer is 2. Okay. All right, awesome. Let's go ahead and take a look at part B now. Now we're at 2 plus, and so note this is the same thing as f of 2 plus epsilon, right? And so do take note. This minus, it corresponds with this. This plus corresponds with that plus right there. All right, and so now we note that, 2 plus epsilon, well, that's obviously always going to be a little bit more than epsilon. So we're going to be using this guy here, which is just 1. Okay, so that's the answer to that question there. All right, let's go ahead and take a look at a graph of this. We're going to switch over to our Desmos program. And so now we had x minus 2, quantity squared, negative in front, plus 2. And this was true as long as x was less than or equal to, let me go back to where we were, less than 2. So it was true if x was less than 2. And then y, it was 1. I got to use a different letter for this one, or else I'll confuse the program. As long as x was greater than or equal to 2. All right. Let's go ahead and fix the scaling here so we can see it. There we are. So you can see clearly as you approach from the left, it equals 2. And as you approach from the right, you equal 1. All right. All right, infinite limits and limits at infinity. Obviously, it's not section 10.2. We're switching books, so I did not get this one changed out. But this is still in chapter 3. All right, if the limit of a function approaches infinity, then it has a vertical line, vertical asymptote. All right, so let's take a look at these. Find the limits of the following functions. So the limit as x approaches 2 from the left. So again, we're approaching 2 from the left, like this. You note that we've got this line here, because it does appear to be approaching infinity as we go up along here. And so we'd say that is infinity. You note that if I approach from the other direction, the result would have been the same in this case. And so we'd say there is a vertical asymptote at x equals 2, right? Because it doesn't matter what y equals, x always equals 2. All right, so now here, note it's the exact same equation. This time there is no positive or negative. This means that it is a two-sided limit. You note that we do have a vertical asymptote here, and it doesn't matter if you approach from the left or the right. The result is still the same. You are approaching infinity. And if, on a related note, if you approach a function from the left or the right and you get the same result, then you can always just simply write it as a two-sided limit. Okay, and this one, as we approach 2 from the left, what's going on here? Well, we're plunging down towards negative infinity. Okay, so now let's go ahead and put on our thinking caps for a second here. Hopefully they've been on this whole time. What if we approach from the right? Would it be negative infinity? Well, you might be tempted to say that's the case, but note the function is not defined after 2, so we would simply write undefined. We know where it's approaching from the left, but not necessarily the right. All right, and so these are, examples of how to work with if a finite limit, when I say finite, I mean like a number. If a finite limit approaches infinity, then you have a vertical asymptote. Now what about if we take a limit that tends towards infinity, right? That is, we take the limit as x goes to infinity. That's what that means. And then we want to write it as, well, okay, got to jump the gun there. As x goes to infinity is how you would write that one. All right, and so if this limit, if it approaches infinity, then we say the function diverges. And if this limit approaches a number, then we say the function is convergent. That is, it's approaching a value. Diverges means it just shoots up wildly up towards infinity or down towards a negative infinity. All right, so let's evaluate the following functions and state whether they are convergent or divergent. All right, this one. The limit as x goes to infinity, well, you can see that it is shooting downwards, plunging towards negative infinity. So we would say it is divergent. Okay. Here, limit as x goes to infinity, well, we're going way out this direction. Certainly looks like it's approaching 1, so we'll say 1. So we say that it is convergent. Note that if we were to go in the other direction, that does seem to diverge. So as you go to the left, it converges. As you go to the right, it diverges. All right, okay, same one. Okay, so as x goes to infinity, we're shooting up towards there, and so it is divergent. All right, good. All right, let's keep going. Now we've got a few values here. All right, so let's go ahead and work these problems here. We've got e to the x. And so when you're, a trick to kind of see what's going on is, and this works if the function is continuous at the point you're evaluating, but you just plug in e to the infinity. And so you may not be familiar with the shape of e to the x. You should be, but if not, that's okay. If you don't immediately see what the graph of e to the x looks like, pause the video and graph it in Desmos.com right now, and just kind of just try and get a feel for it, because this is one that you absolutely should have memorized, like the shape of the graph. It's very, very important. So again, if you don't have the shape of this graph memorized, pause the video, go to Desmos.com. I can write it better. Desmos.com. Handout.com and graph it and look at it and make sure you get that shape memorized. All right, so, but even if you don't have it memorized, you just gotta, if you think through it, the answer to this one should be pretty obvious. Because what we're really saying here is we've got an e, which is just a positive number, 2 point, then a whole bunch of decimal places. A lot like pi, but then we multiply it again, and again, and again. And how many times do we do this? We do this an infinite number. Then times e, right? So if I multiply any positive number by itself an infinite number of times, well, it's got to be infinity, right? Just logically thinking it through. And so we would simply say that is infinity. And that's it. And so this would be a divergent function. All right, so this next one, let's take a look here. Again, we're going to just plug in infinity to see where we land. And we get infinity plus 1, infinity squared plus 1. So this ends up being an infinity over infinity. This is undefined, right? You can't say infinity divided by infinity. So we got to be a little bit smarter in this one. So we can't quite do it this way. So instead, we're gonna massage the value a little bit. And when I say massage, I mean simply we're going to change the form in which it appears. We are not changing the actual value. Okay, this is not we're not doing the books for Enron here. So we want to do everything properly. So we have here the limit as x goes to infinity, and we're going to divide everything by the lead term at the top here. We're going to divide everything by x. Okay, so you divide everything by x, right, top and bottom, and you'll get 1 plus 1 divided by x, and the bottom, x squared divided by x is just x, and then we got plus 1 over x, right? That's all we're doing. We're just multiplying top and bottom by x. That's it. Nothing more. All right. Now let's go ahead and plug in the limit and see what happens. We got 1 plus 1 divided by infinity. And in the bottom we've got infinity plus 1 over infinity. All right, so let's take a look at this one right there. 1 divided by infinity is going to be a very small number indeed. In fact, one could say it is vanishingly small, much like our epsilon. So we can just say that, well, that's, approaching 0, right? Technically it's approaching epsilon, but epsilon is approaching 0 as well. So we just call that 0. Same right here. We'll call that 0. And so what are we left with? Well, we're left with 1 divided by infinity, right? From over here. And that's also just 0. I mean, if you want to be technical, we'd say it's epsilon, which is basically 0. Now, the advantage to writing it like this is that this will tell you that as you're going way off to the right, you are approaching 0, but you'll be approaching 0 from above, not below. If this were negative, you'd be approaching it from the bottom. Okay, so that's a nice piece of information that we can have. It'll help you understand some of the problems. The important thing I want you to know about this, though, is that this does equal 0. That's the really important thing. Knowing this is just gives you the extra step. All right, so now let's take a look at this one here. Now we're plugging in negative infinity to this value. And when we do that, we put negative infinity plus 3 quantity squared. All right, so if I take 3 away from negative infinity, well, it's not going to make a big difference. As a matter of fact, it makes no difference whatsoever, because you can take 3 to the right of negative infinity. Well, infinity just keeps on growing, so it doesn't care. All right, so Now we're left with negative of negative infinity squared. The squared does have an impact, right? Infinity times infinity is still infinity, but the negative sign is going to become positive. So we're left with negative infinity like that. So the answer is simply negative infinity. Okay. Awesome. Oh, and so this one is convergent, and this one is divergent. All right. And that's it. That's the first lesson. I hope this all made a lot of sense to everyone. I do strongly encourage you to hop onto Desmos and graph each of these problems here. It'll help. Getting that visual will definitely help you see what's going on, as well as get you a little practice with that website, because we will be referring to that one quite a bit throughout the semester. Well, anyways, I hope you guys have had enjoyed listening to me. And I hope, but more importantly, I hope you guys have learned something from this. If you have any questions, don't hesitate to email me. I will do my best to answer them right away during my office hours. If you email outside of office hours, it might be a little late, but I will respond to your questions. So, have a good day.